Hi, today I would like to share with you a robust hybrid state estimation using weight-least absolute value method. State estimation is a central and fundamental unit in power grid operation. It takes in grid measurement data to output the estimation of state variables using an optimization problem. The solution is then used in many analysis and decision-making processes. When state estimation is not reliable, it will lead to a wrong power flow simulation, wrong contingency analysis, and even wrong control decisions, because all of them are based on state estimation solutions. However, the quality of state estimation can be indeed affected by bad data. The traditional state estimation uses weight-least square method. This is not a robust estimator. Every time after state estimation, a separate bad data detection step is needed to detect and localize bad data by checking residuals. This is an iterative process of doing detection and rerunning state estimation until there is no bad data and the solution looks trustworthy. Later on, to build robust data estimator, some researchers use least absolute value, which can reject bad data automatically. However, the methods are convex only for PMU data, and when conventional scatometers like RTU exist, the hybrid state estimation problem is nonlinear and non-convex, therefore it's not tractable. Other methods for convex state estimator also exist, like semi-definite programming, but those methods do not work well in large-scale problems. To overcome these limitations, in this work, we want to build an AC hybrid state estimation that is robust against bad data, but also convex and scalable. The figures in this slide show some of its advantages from the optimization viewpoint. Here we plot the contour of the objective function and also the solution trajectory in different methods. The two figures above show the problems with weight-least square method. Here the hybrid state estimation is nonlinear and non-convex. We have the trouble of getting stuck in a local optimum or saddle point. On the right figure, when bad data exists, the traditional method has no robustness, and even if it converges to a global minimum, there is still a deviation from the true state due to bad data. By contrast, when we convert the proposed method to an equivalent form and plot its objective function, the use of weight-least absolute value makes the objective function non-differentiable, so the contour has corners. Compared with the traditional method, our approach is convex. It has only one global optimum. When bad data exists, on the bottom right figure, weight-least absolute value captures bad data and we reach a solution at the corner that is still close to the true solution. Meanwhile, the zero injection loss constraints in our approach act as the blue line in this plot to constrain the feasible region, and it also helps make the solution more accurate. Now let's go to the main idea of the methodology to see how we get these nice properties. According to substitution theorem, any component in the system can be replaced by another circuit element that makes the voltage or current across the element equal to the voltage or current in the previous network. In this work, what we did is we built linear circuit models for different types of measurements, conventional RTU meters and PMU meters. In these models, we added a noise term N to represent possible measurement noise and error. Now we replace those measured components with the linear circuit models. By substitution theorem, the original power system is mapped to a linear circuit system as in the middle figure. And with this linear circuit, we can then formulate a convex state estimation problem by minimizing the weight-least absolute value of the noise terms, subject to network balance equations at all buses. This is a robust state estimation because by assuming that bad data are sparse, the use of L1 norm enforces a sparse vector of noise terms to capture the bad data. Also, it is clear that since network constraints of a linear circuit are all linear constraints, this problem is a linear programming problem. It has a convex nature. Now we look at how the problem can be solved. Basically, a linear programming problem can be solved by many general tools. One is the simplex method, which works by traversing through vertices. But the problem complexity is known to grow exponentially with problem size. Another method is interior point method. The existing general toolbox of interior point method work for both convex and non-convex problems. In order to guarantee convergence for any general tools, for any general problem, there are a lot of filtering and line search mechanisms being used in existing tools. In this work, however, taking into account that the problem is already convex, we can move away from the general tool to design our own interior point method to speed up convergence. Specifically, after converting the original problem to an equivalent form, which is differentiable, we solve its KKT conditions using primordial interior point method. To guarantee but meanwhile speed up convergence, we use what we call variable limiting heuristics in each iteration. The main idea is we start from a feasible solution and we limit the steps of each update, making inequality constraints hold throughout the solution trajectory. Using our proposed method and the proposed solver, we want to show some results to justify the properties of robustness and scalability. First, we test on a small 14-bus case. The test case is measured by a set of conventional RTU meters, and we created bad data on bus 6 and bus 14. The results show that in our weight least absolute value method, the vector of noise term is sparse, and the large non-zero noise terms correspond to the locations of bad data. However, the weight least square formulation using the same models cannot give a sparse solution to clearly indicate bad data. And meanwhile, we can see that weight least absolute value method gives a smaller mean squared error, meaning that this is more accurate. And this is because the impact of bad data is captured by the sparse residual, and bad data will not affect the solution. Further, we test on larger networks to show the efficiency of our proposed solver. We can see in the right table from the results of work time and number of iterations. Simplex method cannot work well in large networks. The number of iterations grows drastically and it fails on larger networks. The general interior point solver is better, but it remains time consuming due to a lot of line search mechanisms. In comparison, our proposed method takes less time to solve and ends up more efficient. Finally, apart from being robust, convex, and scalable, the proposed method using circuit-theoretic approach is applicable to both transmission and distribution grids, as well as generalizable to parallel computing techniques, because the entire system is separable to several subnetworks and they can be solved separately. These benefits have been demonstrated in our recent work. So this is all my presentation, and if you have any question, please feel free to reach me.